Okay, on our Schmitt trigger circuit here, the last time we left off here, we had a standing voltage, an idle voltage on the output here. Remember that 2.4 volts roughly? And that's the result of the design of a Schmitt trigger circuit, that whatever your input voltage is, your threshold voltage, your standing voltage is going to be a little bit in that range there, in this case 2.3 volts. My threshold voltage is designed for 3 volts, and because we had this in saturation, the collector is going to be a little bit lower than the base, and about 0.7 volts lower in this case. So we're always going to have a standing voltage, and we want to drive a load from ground to positive voltage. So we have to design a circuit that's going to take the standing voltage and take it back to ground, and at the same time be able to match the impedance, because we have a 1K ohm resistor in here, and that's not going to run a motor too well at all. We need to get this down very low, almost to a transistor driving a motor. So if we have to match this impedance as well, so we have to design a circuit that's going to match the impedance from a high impedance output from here to a low impedance load, as well as drive the load from ground to positive supply. And that's what's coming up next. First of all, we're going to run a motor, small little DC motor here, around 400 to 500 milliamps. We'll call that 500 milliamps for right now. We're going to have a 10 ohm resistor in series with it, because we want to use that resistor for a feedback resistor later on in the design. And we want to drive this through a transistor, NPN transistor, directly to the positive side of the 8-volt battery. Now, we can, if we were to put we wanted to put a 10K ohm resistor in here, we want to get the impedance higher than the output impedance here. So we can use a 10K ohm resistor in the base here. That would take care of impedance matching. However, though, again, like we said, we already have a standing voltage here of around 2.4 volts roughly. So we have to get rid of that standing voltage before we can even connect that to an output transistor. So here's how we're going to do this. What we can do is we can take a 10K ohm resistor here. That gives us a higher input impedance with respect to the 1K ohm output impedance, and we can drive a transistor, an NPN transistor, and let its collector go back to the positive side of the battery. Now we have 2.4 volts at the base. What we need at the emitter then, we need this transistor to be at cutoff until we get a valid signal in here, until this goes to 8 volts. So if we put a resistor at the emitter here and another resistor to the positive side of the battery, and we put this resistor down to ground, we can form a voltage divider here, and we can design this voltage divider to have 2.4 volts at the emitter. That would put it at cutoff, because the emitter and the base are at the same voltage value, and that would cause the transistor to be at cutoff, waiting for an input signal come in that would raise the base voltage up, and then it can start conducting. We can let's go ahead and figure out what resistor values we can use here to do that. As to not use up the battery voltage, we can put a 10K ohm resistor over here on this side, and now we need to figure out what resistance value we will need here, and we can take the 8 volts here, and we can rearrange our equation and solve for RE once again. We'll call this RE. If this is Q2, we'll call this Q3. We'll call this RE3 for right now. And so we'll use our voltage divider equation, and we will solve for RE3. That will give us 2.4 volts dropped across it. Get our original equation here. We can use this equation right here. RE equals the emitter voltage, which in our case would be the 2.4 volts that we have here. RC2, in this case, we'll be using that their 10K ohm resistor, and we can then use this equation here to figure that value out. So let's go ahead and put that back on here, RE. equals VE, and we'll go this times 10K times 10K divided by our 8 volts VCC minus our VE value of 2.4 volts. And VE here is 2.4 volts. Alright, let's go ahead and figure this out for RE here. Okay, that gives us roughly around 4.2K. 4.3K would be a nominal value. So we'll go with 4.3K and see what that comes out as. 4.3K right here for right now. Okay, now we're going to solve for the amount of current that's going to flow through here. Because with this amount of current that flows through here is going to be a signal current or a driving current for a PNP transistor, because we have a negative going signal coming out of here now, and we need a positive going signal to drive the base of this transistor. So we'll have to put a PNP transistor in between here. So let's figure out how much current that's going to be flowing through here now under this condition. Okay, that would be 2.4 volts at the emitter here. 2.4 volts divided by our 4.3K. And that will give us our emitter current here. Give us 558 microamps flowing through the emitter. Now we need to couple this signal now. Whenever this base voltage goes to 3.1 volts and this remains at 2.4, this will start conducting, and this will start conducting at 558 microamps, and we're going to pull some of that current from there into a PNP transistor now. And this PNP transistor is going to drive a positive signal into the base of the motor driving transistor right here. So let's figure out now what resistor value we'll need going into the base of this transistor here now from here. Okay, under this condition here, what we need to do is we need to remove any positive line from this transistor here. That can't be there. That has to go directly in like this here so that we have current flowing. Okay, so what we have now is under the condition where the base voltage here goes from 2.4 volts and goes 0.7 volts higher, around 3.1 volts, and we have this sitting right here with this here voltage divider at 2.4 volts at the emitter. Then with this 4.3 ohm resistor in here and 2.4 volts here, we're going to have around 558 microamps flowing through the transistor here now. That current is going to flow into the base of this PNP transistor, and if we assume a beta minimum of around 20 for this transistor here, just for calculation's sake, we can solve now for the amount of resistance we want the base here and how much resistance we want here to drive current into the NPN transistor here that's going to drive the motor load itself. So let's figure this here out. If we have 558 microamps flowing into the base, if we assume a beta of 20, we're going to take 20 times that, and that's going to be the current that's going to be flowing out of the PNP transistor. Okay, the best approach to do this here would be just to put a 1K ohm resistor at the base of here and put it right here, 1K ohm resistor, just for some current limiting into the base. That's all that's for. That's all it really takes. So now we're going to go ahead and build this now, and we're going to check to make sure that we have our standing voltage here and make sure that our transistor here is in cutoff until we get a valid signal in the input here, and this rises to around 8 volts. And when this rises to 8 volts, then we will get a negative signal through here driving this PNP transistor, which would in turn go into saturation and bring a positive input to this NPN transistor here. Should bring this motor to turn on then through maximum current flowing through it. And then we're going to put a signal here, a sine wave, and convert all this to pulse width modulation and drive the motor load under pulse width modulation as well. So I'm going to go ahead now and build this circuit here now, adding it on to the original circuit over here. Okay, here's our NPN transistor now. That's going to match the impedance of the output here to the load, and that's right here going in now. Here's a 10 ohm resistor here to drive the base of this transistor over here. What I have built so far is I have the transistor, this transistor right here in the circuit, the base connected to the output of the Schmitt trigger, and I have its emitter connected through the voltage divider here, consisting of a 10 k ohm resistor to the positive side of the battery and 4.3 k to ground. And I'm going to check now a measurement here at the emitter and see if we're getting close to 2.4 volts. That matches our base voltage. Okay, now this is the base voltage right here, and now we're going to check the emitter voltage. Okay, we're looking good. 2.4 volts on the emitter and 2.47 on the base. So we are now set for having this transistor at cutoff right now. So this transistor is at cutoff, so now we can do is connect its collector to a PNP transistor and then connect that to a driver transistor to drive a motor. And that's coming up next now. Okay, just through some experimenting here, I found out that this transistor here will be driven by a 470 ohm resistor. 1K just was not enough to do that, so a 470 ohm resistor worked really nice for this. So now we have this transistor here, which is biased at cutoff until we get a valid signal in here. And then this transistor begins to conduct once this base voltage goes to about 3.1 volts or higher, and it conducts current in the PNP transistor, which then allows its current to flow through this 470 ohm resistor into the driver transistor here for the motor, and this transistor here turns on and turns the motor on. Now this transistor will never go into saturation because the collector voltage will always remain higher than the base voltage because there's no resistance here. But it does go on enough to drive the motor load. So what all this here does now is this matches the output impedance of the Schmitt trigger circuit, which is a high 1 k ohm impedance plus a standing voltage of 2.4 volts. This circuit takes the voltage and brings it back down to a ground for the motor to be run from ground now instead of from a voltage above ground, which would be over here. We're now got it back down to ground, so the motor is now running from a ground voltage to positive side of the battery through a transistor driver. And at the same time, we also match the high impedance output of the Schmitt trigger to the low impedance of the motor itself here. And so that's what all this circuitry was doing here. Now we're going to go ahead and put this through a test. I had the motor set up right here. This is the input voltage to the Schmitt trigger circuit. This is the output voltage across the at the output of this transistor here on this side of the motor here. And what we're going to look at is, with no input signal from the oscillator, just pure input signal from the potentiometer itself, we're going to see how the motor has no variable voltage to it, has no variable speed because we're going from low to high. So as I turn the potentiometer here now, the input voltage goes up to about 3 volts, and we're at maximum now across the motor. As you can see, it's going maximum speed, and that's the maximum that we're going to get at the motor. Okay, if I turn the potentiometer back down again, it goes right off. It's either on or off, on or off, nothing in between. Now we're going to put our input signal to there now. Now, as you can hear, the sound of the motor. Okay, so now we have, once again, we have our, here's our input, here's our output, both on DC. Okay, now we're going to raise our input voltage now. Now we can actually vary the speed of the motor through pulse width modulation now. There's the voltage at the output now, the input voltage. Now I don't have the oscilloscope hooked up yet to the output here, so let's go ahead and hook this up here now to the output. And there's our square wave. Let's get rid of the input here. There's a square wave across the motor. As you see, it's getting larger, it's smaller. There's maximum speed. And we can get down to a lower speed. According to our pulse width. So what we're doing now is we're running a motor load now off our Schmitt trigger circuit at pulse width modulation. Again, there's our input. That's our output across the motor. Right there is full voltage. And now we can vary that voltage a little bit at a time because we're now using pulse width modulation. We're no longer using this as a switch, but rather as pulse width modulation now. See, I'm way down there now on the output. And I'm able to vary the speed of the motor very, very slow because we're using the pulse width modulation method. Okay, that gives an idea of how to match, to be able to match the output of a Schmitt trigger circuit to a load that needs a low impedance load as well as a ground reference load. And we learned how to design a circuit that would match that now and make it work properly. Alright. Okay, that explains it, and I think we got a good demonstration here of this circuit now. The next demonstration will be to design a oscillator to run all this here, and then we can put this away and make our own oscillator to run this. And that'll be coming up later on in the next series, next video. Okay, thanks for watching. Bye.